Hello, welcome to our ESC 448 hover project by Tony Sancho and Luke Solons. The objective of this project was to create a state estimation and state feedback control mechanism to keep the quadcopter in quasi-steady flight at constant altitude with no XY motion and minimal yaw rate. To do this, we had an overall architecture that looked kind of like this. So starting in the blue box, we have the overall mission controller, which we'll go into more detail later. The small green box over here is where the sensor data and optical flow data come in. Next, in this rudder area, we have the 4 different control loops: the throttle, elevator, aileron, and rudder loops. These inputs come from the sensor and optical flow data we talked about earlier, and the set points are controlled by the mission controller. Over here, the throttle enable and throttle offset commands from the mission controller are set in the switch, and then the summers at the end of each of these subsystem blocks is to add in the steady state offset values that we'll go into more detail later. Lastly, the TEAR inputs are converted to motor frequencies using the motor mixing matrix before they're spat out at this output here to the motor speed. So the throttle, elevator, and aileron loops had architecture look kind of like this. So again, we have the optical flow data and the sensor data coming in on the left. Unneeded inputs are terminated, and those that we do want next go into this green area where they're processed, which we'll go into more detail later, and get rate transitioned so that match what the Kalman filter expects to see. Next, in this pink area is the actual Kalman filter, which is based off of matrices designed in the Homework 4 assignment. And then the estimated states come over to the robust servo mechanism LQR controller, which we covered in more detail later. The integral control path and the state feedback control path are then combined in standard RSLQR fashion and spat out as the T output. Similar things occur for the elevator and aileron loops, the only difference being the states or the sensor data used and optical flow data used. The rudder is a little bit different. So instead of having a state controller, it's just a basic integration of the rudder to, or the yaw rate to maintain that to 0. So again, sensor data comes in on the left. It gets converted in this R fixing thing to get rid of offsets and whatnot. Rate fixed, basic PI control loop, and then gets spat back out as the commanded motor speed. The flight path controller looks something like this. So in the top blue section here are the 4 different offsets, or the 4 different commanded variables. So we have the Z command, usually set about -1 meter, or a height of 1 meter above the ground. The pitch rate is set to, or pitch angle is set to 0, roll angle is set to 0, and yaw rate is set to 0. There's no way to get a good yaw angle approximation, so regulating the yaw rate is as good as we can do. Next in this green section is the throttle enable control. So when the aircraft is first taking off, the throttle is disabled because of the faulty pressure sensor. And that's what this green area does. In orange is the throttle offset control. So that sets the manual throttle increase to get the drone off the ground. So these two figures show what they do. So it takes about a quarter second for the drone to get high enough off the ground for the pressure sensor to give good data. So at the first 0.2 seconds, the throttle is disabled. Afterwards, it is enabled. Throttle offset, it ramps up slowly to 150 hertz. Instead of doing a sharp increase, which was causing low battery warnings from the drone because of the increased current caused by the motor draw when they start up really quickly, so we did a ramp instead to prevent those issues from happening. Then it's on for a quarter second and then turns off, and the throttle controller itself is allowed to be turned on. Next is sensor calibration and filtering. So all sensors were processed in a sub-block that had this general architecture. The raw signal values entered in the blue block right over here, and then it gets converted into a double in the green section because the drone measures things in singles and all the math we do is double precision. And then it gets passed into a MATLAB script that for the first t average seconds creates a running cumulative average of the sensor value. This is done for increased control over sensor calibration instead of using the black box provided calibration values from the drone. The AVG val output is the calibration value, and the data output is the corrected sensor value. Lastly, the orange section over here applies a low pass filter to remove some noise disabled in the figure 1/1, and the outputs are filtered, calibrated, and sent back out. So you can notice that we have a lot of 2 workspace blocks to allow for comprehensive data analysis while tuning the takeoff phase and controllers. In this particular block, raw data, offset data, and filter data with an offset allow us to visually see phase lag caused by the low-pass filter and quickly detect faulty sensor calibration. For a drone takeoff, just a little more of an in-depth dive. So in developing the takeoff phase, all controllers were shut off in order to tune the TEAR offset speeds to get a near vertical takeoff. Once the drone had a near vertical takeoff with minimal angular rates, the elevator and aileron controllers were enabled in future takeoff flights. As is shown in the top two plots, there is good angle control during takeoff. In the vertical speed plot on the bottom left shows the drone takes about a second to lift off, corroborated by the video that I'll play in a second. And then lastly, the bottom right figure shows how the pressure sensor takes most of the takeoff phase to no longer be affected by the propeller downwash. So when the propellers spin up, it causes a higher pressure below the drone, which tricks it into thinking it's actually going up to about 2 meters and back down again, when in reality it's still on the ground, if not getting lower. So this height data is ignored for the first quarter second of flight. So I will play the takeoff video now. It's in slow motion so we could corroborate the time and data of what we see with what the drone actually does. So you can see the motor spin up, and over the course of a quarter second, it slowly raises up until it's about a tenth to a quarter of a meter above the ground, at which point the throttle controller would be enabled and hovering would begin.
Once the takeoff phase is completed and the controller is turned on, a robust control system is needed to accurately drive the UAV to the desired states. To properly track these commands, a Type 1 robust servo mechanism scheme was implemented. This method forms the control problem in error space and regulates the error between the command and the estimated states to 0. The state vector for the UAV dynamics was augmented with an error state for height, since this is the variable commanded to achieve hover. The new augmented dynamics are described by the A-wiggle and B-wiggle matrices, which are composed of the original system's dynamic A, B, C, and D matrices. The resulting state feedback control law has an additional component which accounts for the integrated error in height. Because this is a Type 1 system, constant height commands can be tracked with 0 steady state error. Using the throttle system as an example, it's possible to design optimal gains for height H, vertical body axis speed W, and the integral error in height, such that the system is robust and has good performance. This optimization depends on the Q and R matrices in the infinite time LQR algorithm. Increasing the Q matrix penalizes the state, and this will yield close command tracking, but may result in large gains. Conversely, increasing R will penalize the control, which results in more manageable gains, but a slower performance. In this system, R is assumed to be equal to 1, and the following analysis was performed to determine the correct weighting for Q. So several values of Q were used in the LQR algorithm to determine the state feedback gains, and these gains were used to form the closed loop throttle system. The system was then excited with a step response, which was meant to simulate a constant 1 meter height command. And these step response plots show the effects of changing the weighting of Q, and particularly shows the differences in response times. Changing the weighting matrix also results in a changing loop gain crossover frequency in the frequency domain. This metric is particularly useful in analyzing the performance and robustness of the chosen gains. While the overshoot and undershoot percentages from steady state remain essentially constant for the throttle system, it's clear that changing the weighting matrix has a significant effect on the rise and settle times. The plot on the left would indicate that the larger loop gain crossover frequencies are more desirable for performance. Another benefit of using LQR to design gains is the guarantee for large stability margins. And in this case, changing Q has little effect on these margins, and both the gain and phase margins remain excellent through the span of loop gain crossover frequencies at about minus 8.7 decibels and 60 degrees respectively. Another important factor in selecting the gains is uncertainty. The equations used to model the UAV's throttle dynamics did not include an actuator model, and so the designed LQR gains did not account for the phase and gain that the actuator might introduce. The actuator can be modeled as an uncertainty in this case, and this would occur between the controller and the UAV dynamics. A delta M analysis model was built by simplifying the preceding block diagram. Small gain theorem states that as long as the maximum singular values of the actuator are less than the inverse of the maximum singular values of the M transfer function, then the closed loop system will be stable. This is a conservative test, meaning that the system could still be stable if these curves overlap. However, separation is enough to prove stability. The rise in settle times and this uncertainty modeling were the only metrics that significantly changed with loop gain crossover frequencies. So these results were used to select a final optimal weighting matrix Q. And this whole process was repeated for the aileron and elevator systems as well. So as an example, this is the selected Q for the aileron system. This is showing the small gain theorem and the uncertainty modeling. So we can see that because the curves don't overlap, stability is guaranteed in the closed loop system. We see here that the step response is as expected. For hover, we would not want a roll angle. So here the commanded angle was 0. And because that's where we're starting from, the simulation shows that it just remains at 0 through time. We can also get the Bode plot and the Nyquist diagrams. We can see we have the excellent stability margins that are guaranteed by LQR. And we have our sensitivity plots and complementary sensitivity plots. These look pretty good too. We don't see any peaking in either plot. And so once the controllers were implemented, it became just a matter of tuning the gains, the filters, and the state estimators. This was a process that we did not entirely complete, although we did make significant progress towards maintaining the hover. One thing that became clear very quickly was that the UAV was susceptible to drift. And upon looking at the optical flow data, it was clear that the sensor was the underlying issue. So you can see here, that's the drift that the UAV was experiencing. And to fix this, a texture blanket was placed underneath the flight area to try and give the optical flow sensor better readings. So after the first few tests, it also became clear that the UAV was reacting rather slowly. This was likely due to phase lag, which was introduced by the filters. Consequently, the low pass filters were made to be less effective, and this helped to reduce such lag, although it also made the system more susceptible to noise. And to try and combat this, the gains were decreased slightly such that the UAV wouldn't make as aggressive maneuvers if the sensors were picking up too much noise. And this is a flight test implementing that.